Swayam Prabha. Digital India. Educated India.
Okay, welcome to this video lecture on basic surveying. Today we are in module number 11 and we will be discussing the lecture number 2. In this lecture number 2, what all we will be covering, we will talk about the curve setting out. In our previous lecture, we had discussed the concept of setting out, why we need it, and we had seen some examples. Then also some basic setting procedures, the use of control points, error sources, and concept of permissible error. Now today in the curve setting out, we will see why the curves are required. Of course, you should be knowing it. Then some types of the curves, the terminology or the definitions which we use here. Then we will see setting out of a simple circular curve. What are the various methods? So now we go for curve setting out. Okay, to begin with, first of all we will discuss that why the curves are required. Think of some engineering projects, for example a roadway. In the road, what happens? The road is coming here and it has to change its direction, because roads, they do change their direction because of many reasons. Now when there is a change of direction, we would not like the road to change the direction suddenly. For example here, if there is a road coming here and it goes like this, we need to change the direction. So this is really not desirable. We know for the obvious reasons. So in this case, what we'll need to do, we'll need to introduce a curve in between so that the change in direction is realized, but the change in direction is gradual. It's not sudden change. That is something which we need to avoid. So this is true for the railways also. This is true for the oil and pipelines or the canals. So for varieties of applications where something is being transported through a corridor, and for changing the direction, we need to provide the curve in the particular structure. Also you might have seen in some, for example the buildings, many times the buildings have got very beautiful curvilinear shapes. So the architect had given the design like that. So it's the job of the site engineer to implement those curves there in the field. So there also we need to set out the curves. What we will do now, we will look about the types of the curves. Well, very first type is horizontal curve. Horizontal curve means the change in direction is in horizontal plane. Okay. The other possibility of the curve is vertical curve. In case of horizontal, these two lines are horizontal, and this is how we need to introduce a curve in the horizontal plane. Now in the case of the vertical curve, we have a road segment here, another road segment, and then in between we have, for example, the railway line. We need to provide a flyover. So this flyover is an example of the vertical curve. So many times we need to provide these vertical curves also. And very often you will find many curves are a combination of these two, vertical and the horizontal curve put together. Well, next, let us look about some further types of the curve. Very first one is simple circular curve. Now what is the meaning of this? The meaning is in between two tangents, because these are called tangents, the road which is approaching and the road which is leaving. In between we have to change the direction, so we have to provide a curve in between. If this curve is a circular, is a part of the circle, so we say this as simple circular curve. In the otherwise case, a curve could be combined curve. In case of combined curve, it's a combination of two curves. Here it is the first curve, then the second curve starts from here, and both of these are different radii. For example, here this is the tangent for this curve and the radius here is R1 and the radius here is R2. So this full curve, if I highlight it, curve number 1, curve number 2, so we've got two curves here. That's why we say this as compound curve. Well, next is the case of reverse curve. In the case of the reverse curve, what happens? We change the direction. For example, like this. There is a road which is approaching like this. We need to change the direction, so this curve is provided here, this first curve. Then again we need to change the direction because the tangents are like this. The road, first of all, it is approaching in this direction, then it is going out. Then again we have to change the direction, and finally in order to go there, so what we need to do, we need to provide one additional curve. So that second curve is provided here. So when these two curves of radius R1 and R2, they are provided, and as well as their convexity is opposite to each other. So we say this kind of curve as reverse curve. You might have seen these many times in field, in actual applications. One more type, and a very important one, is the transition curve. Now what is the meaning of transition curve? When you look at the curves we are providing in order to change the direction smoothly. Okay. Now let's take the example of a simple circular curve. What happens in that curve? This is the road which is approaching, and that's the road in which direction we need to go. So this is the road approaching, and that's the road where we need to go. So what we do, in between we provide a curve, and this curve is a part of circle, and the radius is R. Now over here, if I highlight it, along this road, when you are traveling in your vehicle, the radius here R is infinite. But the moment you start traveling over here in the curve, the radius becomes R is R. So what is there at this particular point where the curve starts, which we say point of curve also? At this particular point, the radius is changing from R is equal to infinite to R is equal to R. So there is sudden change in radius. So what is the impact of that? If the radius is changing suddenly, the radial acceleration, you are sitting in the vehicle, initially the radial acceleration is 0. You are moving in a straight line, and suddenly you start moving into a curve. So there is a sudden change in the radial acceleration. Again, this is not comfortable to the passengers. Similarly in other applications. So what we need to do, we need to provide a curve which changes this radial acceleration from 0 value to a particular value. So how it can be done? In order to do it, what we can do, because our idea is we want to provide a circular curve in between. However, let us do it this way. I provide one extra curve, and this extra curve has a property that at this point its radius is infinite, while at this point the radius of this curve is R. So this is, what is this curve doing? This curve is changing the radius from infinite to R value. So now the change in radius is gradual. So this is why we say it as transition curve. So this is for the comfort. This is for the less wear and tear there in the vehicle. Now let us look at some definitions. Because before we go into curve setting out, we need to see these definitions. First of all, what is back tangent? Over here, this is the road which is approaching, and that's the road which is going out, and in between a curve has been provided. That's the curve. So this curve, or the circular curve, this circular curve here has a tangent. So this tangent is called the back tangent, while when the curve, when you are leaving the curve, so that's the direction of the leaving the curve. So this tangent to the curve is called forward tangent. The point where these two curves intersect, because you can notice here, that's the point where these two tangents they intersect, is the vertex. It is recorded as V also, or it is also called point of intersection. Then we define intersection angle. As you can see, this external angle here is called intersection angle. We will need this intersection angle later on when we set out the curve. Next definition is point of curvature. What is the meaning here? The point of curvature means the point where from the curve starts. So that's the point from where our circular curve starts. So this point we say as point of curvature. The curve terminates here, and from here another tangent starts. So we say this as point of tangent. Then we have tangent distance. What is tangent distance? The distance from point of curve to vertex. This distance is capital T. We represent it like this, and this is called tangent distance. Then external distance is the distance from vertex to the middle point of the curve. This is the external distance. Then we have a term called long chord. Long chord is, I will show it by red color here. If you join point of curve and point of tangent, so this is the chord on the curve, so this is called long chord, and we show it by capital L. Then mid ordinate, we will need all these in setting out the curve. This is why we need to discuss this. This is M. M is mid ordinate. Well, the next is length of curve. Length of curve, we write it as small l, and this is the length along the curve. So this is not equal to capital L, because the capital L is long chord, the distance along the chord. So length of curve is distance along the curve. Then we also define right hand curve and left hand curve. What is the meaning? The meaning is, if you are approaching a curve, for example, we are approaching a curve here. Now this curve could have gone in this direction or in this direction. So there are two possible ways. So if it is going towards my left, we say this as left hand curve, while in this case this curve is going towards the right hand side, so we will say it as right hand curve. Okay, now some more definitions, and this is regarding the designation of a curve. Now first of all, we'll see what is the meaning of designation. You know, whenever we are talking about a curve, we need to say something about the curve. Okay, we can say about its size, about its curvature. So how can we do it? Well, the very first possibility is, about a simple circular curve, we can say about its radius. What is the radius of the curve? So radius is the one parameter which is used mostly in order to designate a curve. The second parameter, which was used earlier mostly, and it was useful in setting out the curve, is also called degree of curve. So radius of curve is very well understood, and the curves are designated by their radius. Now what is degree of the curve? Now degree of the curve is, if for a curve, let's say this is a little part here, I will highlight this. This is a circular curve here. Now for this circular curve, because it's a circular curve, of course it's a part of a big circle, and over here is the center of the circle. For a given arc, if I show that arc here, for this given there is a chord. Now for a given length of arc or chord, what we can say, 30 meter of arc, or we can say 30 meter of chord. For any of these, this distance is 30 meter, either arc or chord. Whatever is the angle made there at the center, that we represent as D, and this is called degree of curve. So this is also one way of designating a curve. So the definition could be whether we will have to ask whether the definition is for chord or whether it is for arc definition or chord definition. So we can designate a curve by its radius and as well as by the degree of the curve. And why I am using this 30 meter here? 30 meter is used because mostly earlier the chains or the tapes, they are of 30 meter length. And whenever we are setting out a large curve, in setting out the chords that we take there are of order of 30 meter. So that is why the degree is defined by this 30 meter. If it is defined by some other, generally if there is no other information given, you can assume it to be 30 meter. And if some other length is used, for example 20 meter, 10 meter, then this information should be provided. So accordingly, we will understand what is the relationship between degree of the curve and the radius. Well, some more terms here, and these are, we say, elements of a simple circular curve. What are the elements? The very first element is length of curve. As we know, the length of curve is starting from point of curve to point of tangent. These 2 points, point of curve and point of tangent, are also shown by T1 and T2. Very often you will find it like that, T1 and T2. So this distance is length of curve, and you can very easily calculate that length of curve is given by 2 pi r by 360 into alpha in degree. What is the alpha? Alpha is the angle of intersection. So very easily, I am not going to derive all these formulae over here, but you can easily compute that it should be like this. Then second element is tangent length. The tangent length, we had discussed that it is this particular value which we represent as T, starting from point of curve to point of intersection. And this angle is alpha, so obviously this will be alpha by 2. Over here the angle is alpha by 2, and this is r, the radius of the curve, and this angle is 90 degree because it is tangent here. So you can compute that this tangent length is r10 alpha by 2. The other element of the curve is length of long chord. Now what is length of long chord? Length of long chord is, as per the definition, is starting from point of curve to the point of tangent, and of course you can also compute this as L is 2r sine alpha by 2. This is length of long chord. Then some more things about the curves, because why we are discussing all these things? Because we will need all these terms or the definitions when we are setting out the curve. Because our main aim today is we want to set out a curve there on the field. So before setting out, we have to do some computations, and all these things will be required there. Now some additional things, and these are chainage of tangent points. Now before we discuss this, what is the meaning of chainage? Chainage, as we have discussed before also in our first few lectures when we were talking about the chain. When you measure the distance using chain, then we can say some distance. Okay, there are 5 number of chains and 20 links. If the chain is 30 meter and each link is 20 centimeter, well 5 chains and 10 links means certain distance. This is how the distances are recorded. When still, even if we are not using chain in the field now, still this chainage word is continuing. Well, we are using the tape. So still for the tape also we say the same, distance along a length. What is the distance at a particular point? That we say as chainage. And generally over here also will represent as as I am writing here, I will say the chain edge as n m. This is the chain edge. What is the meaning of this? There are n number of full tapes or lengths or chain lengths and m number of chain links. Okay, we can write this distance instead of nm also as 100.50 meter. No problem. So, and this is also chain edge. Chain edge means the distance along the chain or the length. Well, the chain edge of V is known. Now, how it is known? The chain edge of V, how it is known, we'll see in a moment. If the chain edge of V is known, we know the distance which we say tangent distance. So, chain edge of V is known, so we can compute very well the chain edge of T1 also. So, chain edge of T1 can be computed. Then, what should be the chain edge of point of tangent? Because we know the length of the curve. The length of the curve, we know about it. So, finally, how our road is going? The road is coming from here. Then it is taking a curve. If I highlight by a different color, let us. This is the road. Then it takes a curve and then it goes like this and then again joins the tangent. So, basically the chain edges are being measured along the road. The distances are being measured along the road. Somehow we know the chain edge of point V. This is how we can determine the chain edge of point of curvature, and then you add the length of the curve, you know the chain edge of point of tangent, and so on. Now, let us do the final thing, the setting out. Okay, what I have done here, I have drawn a ground on my computer, on my video screen. So, if you look at the video screen, over here there is a road, and this road starts from a point A and goes to a point B. You can see the point B and point A, and in between this black line is the road. Well, obviously we can see this is the forest area, and over here we have the water body, and this is the terrain. Now, our road has to change its direction because of the topography, because of limitations there. And this road so far is on a map, because we have planned this road on a map. And while we are setting out the road, we are setting out in small parts. So, let us say we are setting out like this. And right now we are interested in this curve. So, the road is a straight road here. The tangent here is this, and that's the forward tangent. And in between we have to set out a curve. So, this is something which is desired. We want to do it. Now, at this stage, what all is known? Number one, which is known, is the chain edge of V. Now, how do we know the chain edge of V? We know the chain edge of V from our design, because we know the chain edge of from the map, from our design. What will be the chain edge of this particular point? From here itself, we know the angle alpha. Now, where is the angle alpha? If I highlight it, over here is the angle alpha. There is the angle alpha, the intersection angle. We also know radius r. How this r is being decided? Now, radius, in between two tangents, we can fit the simple circular curves for different radii. Now, why should we choose a particular one? Obviously, you can start thinking, if the vehicles which are negotiating the curve at very high speed, the curve should have large radius. If the vehicles which are negotiating the curves have got small speed, not very large speed, we can provide even smaller or very high degree of curvature. Still the vehicle will not overturn. So, basically, how this radius is decided? It will be decided based on the design speed on the curve as well as about the topography. Does the topography permit you to provide a particular radius or not? So, considering these things, we decide the radius also beforehand. So we know the radius also. It is known to us. Then first of all, we would like to find where are tangents. We have the location of these tangents on our map. Always in any project, we make the map. In our map, we have these tangents plotted. So what we'll do from the map, as we discussed in our last lecture, we will take the references to the tangent and we will set out those tangents there on the ground first. So the very first job that we do is setting out the tangent. Setting out means we have put some ranging rods there. So we have ranging rods, one over here at the point of intersection, over here and over here. These are the ranging rods. So this is how, by putting the ranging rods, we have now fixed our tangents. Then we would like to determine point T1 and T2. The meaning is point of curvature and point of tangent. How do we do it? How do we locate it? Locating T1 and T2. Once we know this line, we know how much we have to move in order to locate T1. So T1 is here because this is tangent distance T. Then we also move along this tangent to locate T2. So T1 and T2 are located because we know we can do the computation for this distance. Once T1 and T2 are located, let us say the T1 and T2 are located. T1 and T2 are located here. Then we will have to start setting out. So at the moment, if you consider the ground, there in the ground, what we have? There in the ground, we know, okay, point of intersection is there, T1 is here and T2 is here. This is the only information that we have. We have the information about, because we can measure the angle of intersection, alpha can be measured, so we have also that angle with us. We have also the radius of the curve which we want to set out, because the tangent is computed from the radius information only. Now, there in the ground, so far there is no curve, only two tangents. So we need to do something now so that we can set out that curve. So what is that procedure that we need to do in order to set out the curve? This is what we are going to see now, that how we can set out. Now before we set out, one more important thing, and that is called peg interval. Well, before, it is desirable that our pegs are set out at regular interval. What is the meaning of this? The meaning is, if we have a curve and we want to set out this curve, so definitely we will be setting out this curve in some discrete points. So what we want, that the distance between these points should be uniform. And generally for large curves, we would like to have it equal to a chain length or 30 meter. Of course, it depends upon the choice of the engineer who is working in the field. Because for a smaller curve, we would like to have these peg intervals smaller. For very large curve, we would like to have these peg intervals large. So the idea is we want to have these pegs at uniform interval. Also one more thing, as we are discussing the chainage, we want to have these pegs at full chainages. For example, the chainage is n, then n plus 1, n plus 2. We want to have these at full chainages, because that is easy to work in the field. There in the field, when you are working with the laymen, the workers who are working there. We want to provide them the facility so that they don't bother with much of computation. Rather, using one full chain or full tape, they start setting out the curve. They are not doing any computation there in between. So that should be avoided. And because of that reason, what is desirable? The desirable thing is these pegs should be at full tape length, okay, or whatever the interval we have decided, the peg interval, they should be at full peg intervals everywhere. So how it is ensured? Let us say the chain is of point T1 here is 10, 80. Well, what is the meaning of this? There are 10 number of full chains, 80 number of links. That's the meaning of it. So, if I go backward here, my 10th chain was complete here. So, the chain age of this point is 10, 0. 10 full chain and 0 links. Now, rest of this distance is starting from a point here to a point here. This distance is equal to 80 links. So, this T1, I don't want this T1 to be my peg interval. Rather, what I would like to do, I would like to have my first peg interval at a point here, which I say A1, so that the distance between T1 and A1 is equal to 20 links. So, by doing it, what we have achieved, the chainage of A1 is now 11, 0. So, it is a full chain point. The next chain and next point, next point, next point, so that the chainages will be 12, 13, 14, the chains, no links there. So, these are the, this is the how we decide the peg interval. Of course, depending upon the length of the curve, our last chord, because the last chord is this which we are using, or the last arc can be also smaller than one chain length. So, what we see here, we see our first and last chord could be smaller. That's why we see them subchord, smaller than the full chain length or full length of the chord which we have taken, and rest of them are the normal chord. Obviously, because the very first one was smaller, the last one may be also smaller, in between, all separated by full interval or one chain, we can say, or one tape. So, this is why we give them name first and last as subchord and the rest of them as normal chord. Well, having understood this, now we will go for setting out methods. So, now we will see how we can set out a curve. Now, what is known to us at the moment? We know there in the ground where are the tangents, we just discussed. The location of the point of intersection is known to us, location of point T1, that is point of curve we say, that is known to us, T2, point of tangent, that is also known to us. So, there on the ground we have these three ranging rods, we can say. So, basically these two tangents are known to us along with the point of intersection. What we can do, we can stand there at the point of intersection and measure the angle alpha. Exactly what is the value there in the field of that angle alpha. So, now that angle alpha is also known to us, angle of intersection. Next, as we discussed, we have already taken a decision about the radius. What should be the radius of this curve? Depending the design speed, depending the topography, the radius has been decided. So, these are the things which are known to us. Now, the big question is, where is the curve? So, if you look here, we need to answer this question, that where is the curve? Is the curve here, or is it here, or is it here? Where is the curve? Then the other thing, I can stand on T1, the point of curve. Now, where should I go? If I stand at T1, okay, I am standing at T1 and I want to move along the curve. So, which direction should I take? What is direction so that I am moving along the curve? So, these are the things which we have to take a decision on. And finally, if we can do that, we will be able to set out our curve. And of course, as we have discussed, we will set out our curves always in small chords. Now, what are the methods? Let us discuss the methods for setting out the curve. These methods can be categorized as tape method, tape and theodolite method, and finally 2 theodolite method. Now this is depending the application in our hand. What are the instruments available? Many times if your curve which you are going to set out is not a very important curve, you know that the design speed is less there, the curve is small, or it's not very important curve, then we would not like to use very sophisticated instruments there. Rather we would like to just use a tape or 2 tapes, and by making use of 2 tapes we would like to set out the curve. If the curve is sensitive, we want to set it out correctly. In that case, what is important? In that case, the important thing is that we should use better instruments, the precise instruments. So we may like to go for a tape and the theodolite. And when I am saying tape, I mean we can also include the EDMI. Then, if we have, for example, let's say we want to do it very fast, there is a method which we will see, in which we can use 2 theodolites together and we can set out a curve very fast. Also, when I am saying tape or EDMI and the theodolite, I mean total station. We can also set out the curve by the total station. So what we are seeing here, we are seeing couple of methods, very generic methods, and these methods can be generalized, can be made specific then, depending the instrument which is available to you. So it is absolutely depends upon the field. When you are working in the field, what is the requirement in the field? What is the method which you should use? Once we discuss these methods, you will learn that not all methods can be used in all cases. The topography of the field, our movement, the accessibility of the site, this will also control the method. And of course, what are the instruments which are available to you? The time, the resources, everything. So let's discuss these methods one by one. First of all, we say a method to be tape method. Tape method means we are only taking linear observations, only linear measurements are being carried out. And this is generally used for small and not important curves. In this tape method, one method which is called offset from long chord. I should write offsets from long chord method. Now what is this method? In this method, over here is the long chord. That's the long chord which we know about. Now in this long chord, what we do, we measure some distance, as I am saying x, from the middle point. So this distance x is measured here from the middle point here, and at this x, this point, we erect a perpendicular, that's the perpendicular, and along the perpendicular we measure a distance equal to OX, and then this point will be on the curve. Now what is the value of OX? OX is given as this. I am not getting into the derivation of this because this is a very simple derivation and you can arrive at this value very easily. But I will advise you that you please go through some textbook or try to do this derivation yourself. It's a very easy derivation because that will help you to understand it. So this method is offset from long chord. We have done it for this x. We can do it at equal intervals over here also. So by doing that, what we are doing, we are establishing the points on the curve, and then joining these points, we will have our curve set out. So this is how the curve can be set out. Well, in the next method, again it is a method which is, we say, tape method, and in this case we will take the offsets from tangent. So we are taking, mind please, offsets from tangent. Now our tangent is here, this is our tangent. We want to take the offsets from the tangent. So what is the meaning of this? It is possible for us to walk along the tangent. The ground permits this. The first method in this case is radial offsets. Radial offsets means if I'm standing at any point here, let us say we are standing here, it is possible that I can see the center of the curve. We can establish the center and I can look at the center. Well, arranging out there, and I can see the center. So wherever I move along the tangent, from there I can see the center. So I have got a direction now. Along this direction, I measure a distance equal to OX at a distance of X. So our X is, this is X. At a distance of X, we measure a distance OX and this point will be on the curve. So this OX is such that we can compute it. It ensures that the point is on the curve. So what we can do, we can keep moving along and we can keep taking these offsets. Of course, in this case, we should be able to see the center. We should be able to draw a line along the center. If it is not possible to see the center, well, the problem is we have, for example, over there a building, and it is not possible that we cannot see the center. So in that case, what we should do? Well, we'll have to go for some other method, and we can say another method which is perpendicular offsets. Well, in this case, what we are doing, we are, if I remove all of these in order to understand this perpendicular offsets, now we are moving along the tangent. Let us do it here. Moving along the tangent at a distance of X. At a distance of X here, I can erect a perpendicular. This is the perpendicular which I am erecting here. So this perpendicular has a length OX, and this OX is given by this. So if at a distance of X, we move in perpendicular direction by a distance OX, this point will be in curve provided we compute the OX like this. Again, you can derive this, why it is so. So in this case, it is not necessarily for us to look at the center because we are not able to see it. There is a building or some wall or some other thing or jungle. So we are erecting the perpendiculars at X and then setting out the curves. Similarly, this side also. Now here is another method, and this method is offsets from chord produced. Now so far in our methods, we are doing those for smaller curves, and also whenever we are discussing this, or whenever we are working in the field, we have to see whether our ground can support this method or not. Then these methods are not very accurate because if our curve is large, our offset from the tangent will become very large. Measuring that distance, erecting the perpendicular will become a problem. So these methods are for not important curve as well as for small curves. Now here is a method which is used very often for the curves in highways, and over here we don't have any angle measuring instrument, only the tape, but the curve is very large. We can't use any of those previous methods. So what is this method? In this method, well, that's the point T1, and somewhere here is the point T2, and it is our back tangent. First of all, what we do, we take a chord equal to C1, and C1 is what? C1 is our subchord. We know where from this subchord is coming. So we take the subchord C1 and we move along. See, right now we are moving along the tangent. We stretch our tape so that this distance is equal to C1. From there, we take an arc. So the arc is taken like this, and this arc ensures that the distance is also C1. Now on this arc, standing at the point A, okay, now I am at A, I want to cut a distance on that arc. The distance should be such that that the point which I get here should be on the curve. Now how can we ensure it? This can be ensured by cutting a distance which is equal to O1. Now what this O1 will be? This O1 is given here. Again, it can be proved very easily. Very easily we can find it, we can prove it. So what we did in this case, we moved, or rather we took a distance C1 along our tangent, then we took the arc and we standing at the point A1. A1 means standing at A1 here, we cut a distance equal to O1 along the arc in order to get the point A. So this is how we get our first point A here. And how much is O1? O1 is computed by C1 square by 2R. This can be proved very easily from this figure. Once we have done it, our first point on the curve is known. Now what next? Right now you just think, we are standing now on the first point of the curve. At the T1 point, the previous point, we had a direction with us, that was the tangent direction. But standing at this point now, A, we don't have any direction. We can't erect our tangent there because we don't know the curve. So if we do not know where the curve is, we don't have any direction, no tangent direction. So what to do here? So what we do, this chord is extended further. So it is being extended like this. Extended means there in the ground, I have a ranging rod at T1, I am standing at the point A, and this particular direction I am taking it back. So we can extend it by any method. It's a problem of ranging. So we are extending it. So I have extended. Then standing at A, now we have a direction. That direction is AB2, or the direction in which the chord is extended. So standing at B, we take a distance equal to C along this direction. And this C is normal chord. We can write here it as C2 also because the second chord. So we take direction C, and again we take an arc from this direction. This is the distance C2. We take the arc here. Now on that arc we cut a distance equal to O2. What is this O2? If you derive it, you can find that O2 is given by C2 by 2R and C1 plus C2. Again, this is a very easy derivation. So if we cut along this, a point here, so this point B is on the curve. Similarly, now what we will do, we extend this chord. So this chord here is extended further. It extended further, and same process is repeated. So here is the general formula. From any extended chord, so what we are doing, we are standing on a point in the curve which has been just set out. Standing at that point, the previous chord is being extended, and from that extended direction, we are taking a distance. For example, C2 we took and an arc, and then along that arc we are cutting a distance equal to, as we have given here, O2. So this is the general formula for this procedure. So if we are following this, what we are able to do, we are able to set the points all along the curve only by using length measurement. Okay, we are not using any angle measurement still. Okay, now let us look at a method when we have the tape with us and we have also the theodolite with us. Sometimes you will desire it like this because you want to do your curve more accurately. Now in the method which we just discussed, the method of extended chord, if you commit a mistake at any point, what will happen? rest of the points along the curve will be all shifted. So, we are establishing the points in an independent, dependent way. The point number n is dependent upon the accuracy of point n minus 1. So that is the disadvantage there. Now over here, in this method, when we have a tape and a theodolite available with us, so we say this method as Rankine's method. Now what is there in this method? Well, our T1 is known to us. We stand at T1 with a theodolite. So we are using a theodolite at T1 point. We know this point V, the point of intersection, so I can align my theodolite in this direction. So my theodolite can be aligned so that it is looking in this direction, and we can set the angle or the reading to be 0, 0, 0. We know the meaning of it. We can do that. Well, next, if I have taken a chord of C1, this is the first subchord. So we can know the relationship now. If this distance is C1, how much will be the angle here, which we say as delta 1. Delta 1 is the angle made by the chord, let me highlight it, made by the chord and the tangent. That's the angle delta 1. So the relationship between these is delta 1 is C1 by 2R. So once we know our C1, the meaning is our normal chord, subchord. So knowing the C1, we already know R, we can find the value of delta 1. So what we are doing now, standing at T1 with the theodolite, we have set this V, point of intersection, as 0, 0, 0. Now we are setting in our theodolite an angle equal to delta 1. So we are setting that angle in our theodolite. So the moment we have set angle delta 1, now we are looking in the direction of this chord. So we are looking in a direction which I am highlighting here, in this direction. So along this direction, we cut a distance equal to C1. So our first point A is known on the curve. Well, next, what we do, we don't change the position of the theodolite. The theodolite stands there only. From there, now theodolite, if the next chord, we have taken a decision now, our normal chord is, let's say, C2. We can easily compute if it is C2, and for C2, let's say that's the C2, and the angle over here is 2 delta 2. What is it? It's 2 del 2, and what is this del? It is the angle over here made by the tangents, 2 and del 2. These are the angles, and this length is C2. So if it is so, again we can have the relationship 2 is C2 by 2R. Now my theodolite is set in such a way that it is looking at an angle equal to delta 2, which is del 1 plus del 2, meaning the theodolite will look in this direction. So this angle is delta 2. Now we can easily prove here that this delta 2 is equal to del 1 angle and del 2 angle. Easily this can be proved here. So now standing at point T1, we have set out an angle equal to delta 2. Now we are looking in which direction? We are looking in the direction over here. I will highlight this direction. We are looking now in this direction. This is the direction in which the theodolite is sighting. And where are we standing? We are standing right now at A with the tape. We are standing at T1 point with the theodolite, but we are standing at A with the tape. So there is a person who is standing at A, and there is a person at T1 with the theodolite. So from A we cut an arc of distance C2. So this point, second point, which is B, is established there. Well, next again the step will be same. We look again in a direction, so that this direction is, we look along this direction, and this total angle, I am showing you this by this purple color here, it is delta 3. How this delta 3 value will be known? Delta 3 will be delta 2 plus del 3, and we know how to compute del 3. So we know that we have to look in this direction, and then how much we will cut from here? From the point B, because there is someone who is standing at point B over here, he will cut a distance in this direction, which is equal to this particular chord. Well, we can say this chord to be C3. Generally all the chords will be same. So cutting that distance means, we are sighting through the theodolite. Now someone is moving there, taking an arc. The moment he is intersected, because we are sighting through the theodolite, so we are looking in one direction. Now the moment a ranging rod which is taking that arc is bisected, you will say that's the point on the curve. So this is how the points on the curve means a point here, then the next point, then the next point, and the next point, and so on will be established. Now one thing important here, over here all the angles are being measured independently. You can set out the angles independently. So that way this method is better. Then this method is faster also, because we are making use of the angles here. It is also more accurate. Only one length measurement is there. Only one arc is being cut. So this is our Rankine's method. There is one more method which we say as two theodolite method. Now in this case, this is very easy, or rather very fast method we can say. We put a theodolite at point T1, also at point T2. We know the characteristics of a circle, and by making use of that characteristics, what we do, if I set an angle alpha here from the back tangent, so I am looking now, my line of sight is in this direction. So my theodolite is at T1, and that's my line of sight. If I set a theodolite, there is a theodolite at T2, and in that theodolite from the long chord, I set the same angle. So over here also it is alpha, and over here also it is alpha, and if I set the same angle here, they will intersect at this point. And by the characteristics of the circular curve, we know that this point has to be on the curve, the circular curve. Similarly, I can do it for some other angle. So what we are doing, this angle for example is, let us say, beta. So we will take the same angle here also, beta. So ensuring that this point is also on the curve. So by taking these successive angles, one person is doing this angle measurement from the back tangent, theta 1, theta 2, theta 3, theta 4. The other person is doing from the long chord, from the T2 point, theta 1, theta 2, theta 3. And wherever these lines of sights they intersect, we are locating those points there on the ground. And those are the points which are on the curve. So what we have seen today, we saw about the curve, why they are required, the elements of the curves, and then also we saw how we can set out a curve in the field. Now the more important thing about this exercise is, this is just theoretical background or the concept, but we need to do it in the field. If you have an opportunity to go to some laboratory, go to the laboratory, take the instrument, go to the field and set out the curve there in the field. So we finish this lecture here. Thank you.